So I accidentally just filmed myself recording this problem, but it did not film, or I thought I was recording, but it was not recording. So I will be working through it again. So let's start with part A here, and part B will be in a separate video. So we have a stream of nitrogen flowing at a rate of 100 moles per minute. It's being heated from 200 to 100 degrees Celsius. So we can see here that we have an open energy system, which means we are going to be dealing with enthalpy, which also means that we need the CP equation for nitrogen. And if we use table B2, we can get the specific enthalpy equation for nitrogen, since it is component specific. And we end up getting that equation is 0.029 plus 0.2199 times 10 to the negative 5t plus 0.5723 times 10 to the negative 8t squared minus 2.871 times 10 to the negative 12 t cubed. Just a little bit about table B2 and using this equation. So sometimes on exam, whenever you do problems like this, you'll see that these last two terms sometimes don't really account for much when it comes to the final CP value or your final answer. So sometimes during an exam or during problems, the professor may ask you to only use the first two terms or only the first three terms. But if you're not asked to truncate this equation, then you should use all four terms, as it is the right thing to do. But just make sure you read the problem carefully, because you could be doing extra work by using extra terms that you don't need or aren't asked to use. And you'll see that these kind of problems kind of take a lot of time when it comes to calculating the final answer, even though it's a little bit of busy work when it comes to that. So delta H, so the specific enthalpy is going to be the integral from 20 degrees Celsius to 100 degrees Celsius, and CP delta T. So when we plug this CP in here to this equation, we end up getting that delta H is equal to 0.029 T between 20 and 100 plus 0.2199 times 10 to the negative 5 T squared over 2 between 20 and 100 plus 0.5723 times 10 to the negative 8 T cubed over 3 between 20 and 100 minus 2.871 times 10 to the negative 12 t to the fourth power over 4 between 20 and 100. When all of these values are calculated out, you end up getting 2.32 plus 0.0106 plus 1.9 times 10 to the negative 3 minus 7 times 10 to the negative 5. And that ends up giving us a final value of 2.332 kilojoules per mole. Now we want this in terms of a rate. So since we have, so our heat required is going to equal the molar flow rate times the specific internal energy change. So that's going to be 100 moles per minute times 2.332 kilojoules per mole. So we multiply this out, we end up getting that it's required that we have a heat input of 233 kilojoules per minute in order to heat the nitrogen from 200 degrees Celsius to 100 degrees Celsius.